Hello everyone, my name is Brinyang. I am a representative from a team member of Faculty of Applied Science at UITM Cawangan, Sarawak. Today I will presenting our research on the decolorization of acid yellow 23 by Photo-Electro-Fenton process using used alkaline batteries. Massive volumes of UAs contain hazardous substances like lead, mercury, and cadmium, which can contaminate soil, water, and air when disposed of improperly, posing severe health risks to human and wildlife. An example of UAs is batteries. So when batteries are thrown away, they can end up in the landfill, where they can take hundreds of years to decompose. By recycling batteries, we can reduce the amount of waste that end up in the landfill and conserve space for other waste material. Inside the battery, there are graphite rods. This graphite was found to have desirable properties for absorption and its ability to remove toxic dye. So, by recycling e-waste, we can reduce the exposure to it that can cause lung cancer, nervous system infected, kidney failure, and more. The objective of this study is to determine the removal efficiency of acid yellow 23 when used alkaline battery are being used as graphite electrode in photo-electro-Fenton process by using UV visible spectroscopy. This study also aimed to investigate the optimal condition of use alkaline battery as graphite electrode in photo-electro-Fenton process for acid yellow 23 removal. Electro-Fenton is a process that involves the reduction of oxidized species using electron generated through the electrolysis of water. Photo-Electro-Fenton is an enhancement of electro-Fenton that utilizes light to generate hydroxyl radical instead of relying solely on the electrical chemical methods. Based on this equation, hydrogen peroxide is generated at cathode with the supply of oxygen. This peroxide further reacts with ferrous catalyst to produce hydroxyl radical and ferric ion. This ferric ion will regenerate ferrous ion in equation 4 through the reduction process. This ferrous ion will regenerate again hydroxyl radical in equation 2. Eventually, this hydroxyl radical will then react with organic matter and demineralize to produce water and carbon dioxide, as shown in the equation 3. Or in a simple way, we say that it is completely degraded. In this process, there is a multiple pathway to produce hydroxyl radical. In equation 5, ferrous ion will react with hydroxyl radical to produce iron hydroxide ions. In this PEF process, light will react with iron hydroxide ion to produce ferrous ions, then will repeat again in the same reaction from equation 2 until 6. This cyclical process eventually enhances the efficiency of the reaction. This was the PF setup used. Graphite from alkaline battery was modified to 5 cm² using resin. Graphite electrode for both anode and cathode was placed between 1 cm. Fish pump was placed at the cathode to produce continuous oxygen. Magnetic sterile to make sure uniform and homogeneous reaction occur. Sodium sulfate was also introduced in the system as background electrolyte. Applied voltage supply is from 1.5 watt battery. Lamp was positioned 30 cm above the beaker. This lamp considers artificial UV, which has 100 watt power. The optimal condition of concentration, catalyst, and voltage were analyzed with fixed parameter of 3 hours contact time and pH 3. In the first step, we studied the effect of initial concentration using 30, 40, 50 mg per liter concentration of acid yellow 23. The other parameters were fixed at 1.5 watt voltage and 2 millimolar ferrous ion catalyst. Then the optimal concentration was chosen from 30, 40, 50 mg per liter based on the highest removal efficiency calculated from the maximum absorbance obtained from UV visible spectroscopy. The samples were taken at hourly intervals. When the optimum initial concentration of acid yellow 23 was obtained from step 1, the study then proceeded to find the optimum catalyst concentration. Catalyst concentration of 2 millimolar, 4 millimolar, and 6 millimolar were prepared and analyzed. The other parameters were fixed at 1.5 volt voltage and optimum initial concentration from the step 1. When the optimum ferrous ion catalyst was obtained in the previous step, the study then proceeded to find the optimum voltage. The other parameters were fixed at optimum condition obtained in the step 1 and 2. The following voltage 1.5 volt, 3.0 volt, and 4.5 volt were analyzed. The ultraviolet visible spectroscopy can measure the change of the concentration of reactant or product over time. The absorbance value of solution was measured at the maximum absorbance of 428 nanometer for acid yellow 23. Then the removal efficiency of acid yellow 23 was calculated according to the equation shown. We move to the result. For the effect of initial concentration, it showed that with increasing initial dye concentration from 30 mg per liter to 40 mg per liter caused the removal efficiency to increase. Higher initial dye concentration enhanced the interaction between hydroxyl radical and dye molecule and the higher driving force involved, resulting in increased dye removal efficiency. This increase in initial concentration also boosts the interaction between hydroxyl radical and the dye, leading to a greater degradation of the dye. However, if hydroxyl radical becomes saturated, additional dye molecule will not be degraded, and the efficiency per unit of dye will be decreased. This saturation point limits the maximum removable capacity of the dye. Moreover, higher initial concentration result in less light entering the PEF system causes the reduction of the amount of HV reacting with hydrogen peroxide and generating hydroxyl radical, therefore resulted in low removal efficiency of 50 mg per liter, that is 47%. Next, for the effect of catalyst. Catalyst of ferrous ion was prepared according to different concentration, which are 2 millimolar, 4 millimolar, and 6 millimolar, and removal efficiency obtained were 70%, 70.1%, and 74% respectively. The appropriate concentration of ferrous ion in the PEF process is a critical factor. Generally, the efficiency of the PEF process improves with an increased concentration of ferrous ion, as it serves as a potent oxidizing agent capable of breaking down large molecules in wastewater, such as dye from dyeing processes. Increase in ferrous ion catalyst will increase the hydroxyl radical production, as recalled from equation C, and in the presence of light, it will generate more hydroxyl radical through equation 7. For the effect of applied voltage, the removal efficiencies were found to be 73%, 77.8%, and 88.2% for 1.5 volt, 3 volt, and 4.5 volt respectively. Increase in voltage will also increase in the hydrogen peroxide production at cathode and further react with ferrous ion catalyst in equation 2 to produce more hydroxyl radical to react with acid yellow 23. This hydroxyl radical react with ferrous ion catalyst to produce iron hydroxide ions from equation C. So, in the presence of light, more iron hydroxide ion product will react with HV to regenerate more hydroxyl radical as shown in equation 7, which will then provide multiple pathways to degrade the acid yellow 23. The result indicated that the system achieved the highest removal rate of at the 8.2% when the optimum conditions were recorded at the initial concentration of acid yellow 23 was 40 mg per liter, the catalyst concentration was 6 millimolar, and the applied voltage was 4.5 volt. Results obtained demonstrate significant improvement when light is introduced as photo-electro-Fenton in the system. One of the future recommendations is to ensure the efficient generation and maintenance of hydroxyl radical during the process, as their contribution rate is directly proportional to the dye removal efficiency. Next, optimizing electrode material is crucial for improving the effectiveness of the photo-electro-Fenton process for dye removal. Other recommendation is by exploring the synergistic effect of combining the PF process with other advanced oxidation processes can also lead to significant improvement in dye degradation rates. Thank you.